next we are starting with the thermal properties of matter. Okay, and this chapter deals with the relation between heat and temperature, different ways of transfer of heat, etc. Okay, so let's begin. So now see, we measure temperature, right? So why do we measure temperature? To get an idea about if something is hot or cold, if somebody is hot or cold, right? So now, even if we touch some object, still we get an idea of something if some object is hot or cold. Okay, but then our bodily sensations are not reliable, we know that. For an example, suppose what you do is you take ice in your hand, okay, and then you release it and then you dip your hand in lukewarm water, so it will appear hot to you. Similarly, now suppose by mistake you put your hand in very hot water, boiling water, let's say, and then you remove it and put it in normal water, lukewarm water, or even water at the room temperature, it will feel cold to you. Have you experienced this thing? Yes, no? Okay, if you haven't, there is no need to experience, right? So at least the second one. The first one you can. Okay, first one you can try. You can hold some ice in your hand, okay, or put your hand in ice for some time, let's say 1 minute or so, then remove your hand and put it in normal water at room temperature, okay, and it will feel warmer to you, right? You can try that. Okay, so our bodily sensations are not reliable, and that's why what do? We make use of some properties of matter, okay, which are linearly proportional to the temperature. That means, for an example, pressure or volume, if you increase the temperature, there would be increase in volume. Okay, suppose you take some liquid, for an example, mercury. Most of the thermometers, they are made up of what? Mercury. So you take mercury in a tube like this, having very small bore, okay, very thin bore. That means the radius would be very small. Okay, then what happens to this mercury? As temperature increases, the level of mercury goes up and it tells you what is the temperature, right? Okay, so then we have different kinds of scales. So generally used scales are the Celsius scale and Fahrenheit scale. Okay, we measure temperature in what? Celsius. We measure it in Fahrenheit. For example, suppose you're not well, you have a fever, then you say fever is, oh, yesterday I had 102 fever, right? So that 102 is what? It is in Celsius or Fahrenheit? Celsius or Fahrenheit? It is in Fahrenheit, right? Okay, if they say temperature of the surrounding is 27, okay, right now the temperature in your area would be around 27-30, something like that. So it is in degrees Celsius. Okay, when they say 27 or 30, they also tell it is 27 degree Fahrenheit, degree Celsius, right? But generally when we tell about the fever, we say it was 102, 105. Okay, 105 is too much, right? Something like that, but we don't tell the unit. Okay, so unit in that case is Fahrenheit. So these two scales, the Celsius scale and Fahrenheit scale, they are widely used. So we need to know the relation between them. Okay, for that reason also, and for the reason that there have been questions based on this thing in the exam, right? So now in order to fix any scale, you need 2 points. One is now commonly chosen points are the melting point of ice, that's 0 degree Celsius, or you can just say it is ice point, because if you cool down the water, then it will become ice at 0 degree Celsius. Okay, so ice point, a freezing point of water, you can say, and boiling point of water, right? Freezing point of water, which is 0 degrees Celsius. Boiling point of water is 100 degrees Celsius. So now you consider temperature at freezing point, temperature at boiling point. You call one temperature something, let's say first one is T1, second one is T2. So T1 you named 0 and T2 you named 100, and the difference between them, it is divided in 100 equal parts. Each part is 1 degree Celsius, right? So in Celsius scale you do that. In Fahrenheit scale, what you do is you say the freezing point of water is 32 Fahrenheit, okay, and the boiling point is 212 Fahrenheit, and now the difference between them is what? It is 180. Okay, I don't know why they did it, but 212, 32, the difference between these two is 180, and then it is divided in 180 equal parts. So each part is 1 Fahrenheit. So 0 degree Celsius means what? 32 Fahrenheit. 100 degree Celsius means what? 212 Fahrenheit. Okay. So then now we want the relation between temperature in Fahrenheit and temperature in Celsius. So then if we just plot these 2 points, so 0 degree Celsius is what? 32 Fahrenheit, and 100 degree Celsius is what? 212 Fahrenheit. So temperature is in degree Celsius is plotted along x-axis, temperature in Fahrenheit is plotted along y-axis or vertical axis. Then 212 Fahrenheit is 100 degree Celsius and 32 Fahrenheit is 0 degree Celsius. So you get these 2 points. You draw a straight line joining these 2 points. Then suppose the temperature is 50. Now you draw perpendicular starting from 50, okay, to this x-axis or Celsius axis, you can say. It meets the graph at this point, okay, and then from there you draw perpendicular on the Fahrenheit axis and you will get the temperature on Fahrenheit axis or in the Fahrenheit scale, right? But then we are not going to do that every time. So we have equation of a line, that is y is equal to mx plus c. This is equation of line. What is your y? Y is temperature in Fahrenheit. Okay, what is x? Temperature in degree Celsius. Okay, when x is 0 means 0 degree Celsius. What is the value of y? It is 32. So c is equal to what? 32. And then what is the slope? So slope is just slope of this line. Okay, what would be slope of this line? So change on the vertical axis divided by change on the horizontal axis. So that is change on the vertical axis is 180, change on horizontal axis is 100. Okay, 100 degrees Celsius is 212 and 0 is 32. Okay, so this difference is 180. Change on the vertical axis is 180 and change on horizontal one it's 100. So divide it 180 by 100, you get 1.8. So m is equal to 1.8, and therefore temperature in Fahrenheit is equal to what? 1.8 times temperature in degree Celsius plus 32. Okay, temperature in Fahrenheit is 1.8 times temperature in degree Celsius plus 32. Is this thing clear, everyone? Is this scale clear? Yes, no? Okay, so this is relation between temperature in Fahrenheit and temperature in degree Celsius, right? Okay, so this thing I have already told you. The Celsius scale, how is it designed? The freezing point or freezing temperature of water is marked as 0 degree Celsius and boiling temperature is marked as 100 degree Celsius. In Fahrenheit scale, the freezing temperature of water is marked as 32 degree Fahrenheit and boiling temperature is marked as 212 Fahrenheit. Okay, after that, we'll talk about the expansion of gases, etc. Okay, so then consider pre-expansion of gas. What is pre-expansion? So suppose you give some heat to the gas and you let it expand freely. Okay, so here suppose there is gas in this container and this is a piston, airtight piston, but then you are not applying any pressure from outside. So what would be the pressure over here? Pressure is just equal to what? The air pressure. Okay, what would be the pressure over here? Pressure is just equal to air pressure. right? You have just kept the piston, just kept it, okay, right? And piston is of course weightless piston, okay, so this is our specialty. Piston is weightless, right? So then whether the gas, suppose you release some gas here, that means for an example, suppose you take some balloon and then you the balloon is filled with air of course, and you just release it, you just open it, then what will happen? So balloon will shrink, air will expand, okay, so it expands in the surrounding. So what's the pressure over there? Pressure is the pressure of the atmosphere, atmospheric pressure. So similarly pressure in this case is also what? Atmospheric pressure only, okay, pressure in this case is also equal to atmospheric pressure only, because you have just kept the piston, okay, piston is weightless. So how much pressure would be there? How much is pressure uh, at outward point? I mean pressure above the piston, atmospheric pressure. Pressure below the piston, it would be pressure of this gas, right? This thing is clear? Yes, no? Why is it free expansion? Okay. So then now there are various conditions. So one is isothermal expansion. So what is isothermal expansion? So here you provide some heat, but walls of this container are conducting. So if they are conducting, that means if there is some temperature difference, what will happen? The energy will flow, the heat will flow from higher temperature to lower temperature, okay. So then what happens is, if walls are conducting, there is slight increase in temperature, the heat will flow out of the container and it will maintain the temperature between this system. This thing is called a system, by the way, we'll talk about that in thermodynamics. Okay, so the temperature inside of this container and temperature outside would be equal, right? So this is called as isothermal expansion, okay. If walls are insulating, then it is known as adiabatic expansion, right? So if here suppose it is isothermal expansion, so then it follows a law known as a Boyle's law. And what is Boyle's law? That pressure of a gas is inversely proportional to its volume, okay. Pressure of a gas is inversely proportional to what? It's inversely proportional to volume if temperature is constant. So in this case the temperature is constant because walls of the container are conducting. This thing is clear? Yes, no? Okay, so now gases follow certain laws, okay, called as a Boyle's law, there is a Charles law, and there is one called as Gay-Lussac's law, okay. So what does the Boyle's law say? So Boyle's law say that pressure is inversely proportional to volume at a constant temperature. We have just seen it. Then there is a Charles law. So Charles law says that if pressure is constant, okay, if pressure is constant, then volume is directly proportional to temperature. So if volume is directly proportional to temperature, that means volume divided by temperature would be a constant, because volume can be written as some constant times temperature. And what is kept constant over here? What is kept constant? Pressure is kept constant, right? So that constant volume by temperature would be something proportional to pressure, right? This is Charles law. And then there is one Gay-Lussac's law that is not written over here, but that says this is similar to the Charles law, but Charles law is related to volume. Gay-Lussac's law says that pressure of an ideal gas is directly proportional to temperature, but what is kept constant there? Volume is kept constant, okay. Pressure is directly proportional to temperature when the volume is kept constant, okay. So if you combine Charles law, Boyle's law, and the Gay-Lussac's law, then what you get basically is the ideal gas law, that PV by T is a constant for any given quantity of gas, right? This thing is clear, okay. PV by T would be a constant, right? because see, Boyle's law says that PV is a constant. Charles' law says that V by T is a constant. Okay, Gay-Lussac's law says that if volume is kept constant, then P by T is a constant. Okay, so what does it mean? PV by T would be a constant for given quantity, given amount of a gas, right? Okay, so what is that given quantity of a gas? So it is, given quantity of gas can be written in terms of what? Number of molecules of gas. Okay, so we say that PV by T would be directly proportional to what? The number of molecules of a gas, right? It's directly proportional to number of molecules of a gas, right? And then uh, then you have, okay, Avogadro's principle. All right, before that, so PV by T is proportional to number of molecules or number of atoms or molecules of a gas. And then now if you find the proportionality constant between them, the proportionality constant is Kb. It is the Boltzmann constant. Okay, the proportionality constant that comes there, it is the Boltzmann constant, right? So what is PV by T? PV by T is equal to Kb times number of molecules, just number of molecules. Okay, so PV can be written as what? N times kBt. So we have PV equals to what? N times kBt, where Kb is the Boltzmann constant, right? So then the Avogadro came and he defined a crucial quantity, crucial term called as mole. Okay, so what is mole? So number of atoms in 12 gram of carbon atoms, it is called as 1 mole of anything. Okay, so number of atoms in 12 grams of carbon 12, okay, the mass number of this carbon is 12, so it is 6.022 multiplied by 10 raised to 23, right? It is equal to 6.022 multiplied by 10 raised to 23. That means number of atoms or molecules in 1 mole of anything would be what? 6.022 multiplied by 10 raised to 23. So 1 mole of a gas is the quantity of gas having number of atoms or molecules equal to this number, which is known as the Avogadro's number. Okay, and then there is Avogadro's principle that 1 mole of a gas will occupy a volume equal to 22.4 liters at STP. Okay, so what is STP? Temperature is 0 degrees Celsius and pressure is 1 atmosphere. That means 1.0 something, 013 I guess, into 10 raised to 5 pascals. Okay, that is Newton per meter square, right? So this thing almost everyone knows that 1 mole occupies this much of volume, right? So then now what you can do is you can write this number of atoms or molecules in given quantity of gas as the number of moles multiplied by what? Atoms or molecules in 1 mole. So any number of atoms or molecules can be written as what? Number of moles multiplied by atoms or molecules in 1 mole. Okay, so n can be written as small n, which is number of moles multiplied by number of atoms or molecules in 1 moles. That is Avogadro's number. If you do that and put that over here, then what do you get? PV is equal to small n times Na into Kb into T, and that Na times Kb is known as the universal gas constant. Okay, it is denoted by R. It is called as the universal gas constant. This thing is clear, everyone? Yes, no? Okay, so what is universal gas constant? Universal gas constant is the product of the Avogadro's number and Boltzmann constant. Okay, it is product of Avogadro's number and the Boltzmann constant, right? And then you get this famous equation. Of course, PV is equal to nRT. Okay, PV is equal to what? nRT, right? So then, okay, this thing is clear, everyone? Okay, so PV equals to nRT comes from ideal gas laws. Okay, that is Boyle's law, Charles' law, Gay-Lussac's law, and then the ideal gas law is combination of those things: Boyle's law, Charles' law, and Gay-Lussac's law, right? That PV by T is a constant, and that constant is found. Okay. All right. Constant is found to be equal to what? N times of R. N is number of moles. Okay. All right. So we have discussed two scales, right? And the temperature over here is taken in third scale called as Kelvin scale. Okay. So this temperature capital T, it is in another scale called as a Kelvin scale. So now what is that Kelvin scale? So see, uh, we have a term called as absolute zero. Okay, a concept called as absolute zero. So now what is absolute zero? Okay, so see here, this is pressure versus temperature graph of three different gases A, B, C, right? So now we know from this law, oh, that's not written, Gay-Lussac's law, that pressure is directly proportional to temperature, right? Okay, we know that pressure is directly proportional to temperature from the Gay-Lussac's law. So if you take some values and you plot that graph for gas A, gas B, gas C, okay, you take some readings and plot the graph, then what will happen? You will get a linear curve. Okay, you get a linear curve. So suppose you start from 0 degrees Celsius and from there you increase the pressure. So you get these kind of curves for gas A, gas B, gas C. They can be anything like hydrogen, nitrogen, oxygen, suppose. So then what you do is you decrease the temperature. So you can decrease the temperature up to some extent and you get some points here also. Okay, but then what you basically do is you get some lines and you trace them backwards. You trace them backwards and then you get miracle of miracles that all those lines they meet at a same point. Okay, all those lines they will meet at a same point, right? So pressure versus temperature graphs of three different gases, they are meeting at the same point, and that point is also along, it is on the temperature axis. Okay, that means pressure becomes zero at the same temperature, right? So we have not made the pressure zero. What we have done is we have traced these graphs backwards. Okay, so they meet at a single point. So that point, the temperature corresponding to that point is known as absolute zero. So same thing will happen for the volume versus temperature graphs also. They will meet at a same point on the temperature axis, and that temperature would also be equal to the absolute zero. I mean, the temperature is minus 273.15 degrees Celsius and it is known as absolute zero. Okay, so what is absolute zero? Basically, we'll talk about this thing in kinetic theory of gases also, but here briefly, the absolute zero is what? The pressure at that point becomes zero, the volume at that point becomes zero, so everything freezes up at that point. Okay, so we call that as zero, and then we define another scale called as Kelvin scale. So the absolute zero is 0 Kelvin, okay, which is equal to what? Minus 273.15 degree Celsius. Okay, and then you take suppose 0 degree Celsius, and what you do is you basically add, okay, 273.15 into temperatures in degree Celsius to get the conversion factor between the Kelvin scale and the Celsius scale. Is this thing clear, everyone? Right? So here the temperatures are measured in what? Temperatures are measured in Kelvin. Okay. In PV equals to nRT. This is not temperature in degree Celsius. The temperature is in what? Temperature is in Kelvin. Okay. Of course you know that, right? Yes, no. In PV equals to nRT, the temperatures are measured in what? T is in Kelvins. T is not in degree Celsius. Okay. All right. So then let's talk about the thermal expansion. Now we know that if temperature is increased, what happens? Solids, liquid, gases, everything will expand. Okay. So suppose, for an example, suppose you take some solid rod. Then this is a solid rod of some material. You increase its temperature and you find increment in the length. Okay. So suppose it is made up of some metal. So then there would be some change in length. Suppose delta L is the increment in length, right? So what would be delta L? Delta L would be equal to what? Length at temperature T minus L naught, right? So of course this delta L would be directly proportional to the change in temperature. Okay, so change in length would be directly proportional to change in temperature. Then change in length would also be directly proportional to the original length. So let's say L naught, right? Because if length is, let's say, 100 centimeters, the change in length is 1 centimeter. So if length is 200 centimeters, change in length would be what? 2 centimeters, something like that. Okay. So therefore change in length is directly proportional to original length also. So you can combine these two, then what do you get is change in length is proportional to L naught delta T. Okay, if you combine this one and this one, change in length is proportional to L naught delta T, and that is change in length is equal to some constant which we denote as alpha. So what is alpha? Alpha is the coefficient of linear expansion. Okay, and then change in length would be equal to what? That constant multiplied by L naught times delta T. Okay, so if you take that L naught on other side, then what do you get is delta L upon L naught is equal to alpha delta T. Okay, so delta L divided by L naught is alpha delta T, right? This thing is clear? Yes, no? Everyone? Is this relation clear? Okay, so then you can write that delta L is equal to length at temperature T minus L naught. Okay, again you can move that L naught on this side and you can find out this relation. So you get LT minus L naught is equal to L naught alpha delta T, which is basically this relation. And then L naught, this minus L naught, if you move on this side, it becomes plus L naught. So you get length at temperature T is equal to length at 0 degree Celsius multiplied by 1 plus alpha delta T. Delta T is the change in temperature, right? So length at some temperature is equal to the original length at 0 degree Celsius multiplied by 1 plus alpha delta T. Delta T is the change in temperature. So you get this relation. Okay, this one is clear? Right? Good. So this is linear expansion. So if you have a solid rod, then it will follow this relation. Okay. Then suppose you have some area like this. I mean, you have a metal plate like this. Okay, you have a metal plate. So then here we need to find out how much would be change in area as we increase the temperature or decrease the temperature, right? So just similar to this, delta L by L naught is alpha delta T. We can say the delta area, change in area per unit original area, is beta delta T, where beta is called as coefficient of areal expansion. Okay, it is called as coefficient of areal expansion, right? And then just similar to this thing, that LT is equal to what? L naught multiplied by 1 plus alpha delta T. You can find out area at temperature T is equal to original area multiplied by 1 plus beta delta T. Okay, right? So area at temperature T is equal to area at 0 degree Celsius multiplied by 1 plus beta delta T. This thing is clear? Yes, no? right? Good. And similarly, we define coefficient of volume expansion. Okay, linear expansion, areal expansion. Next is volume expansion. So delta V divided by V is equal to gamma delta T. That gamma is called as coefficient of volume expansion. And similar to this, we write this relation that volume at temperature T is equal to V naught multiplied by 1 plus gamma delta T. Okay, volume at temperature T is equal to V naught multiplied by 1 plus gamma delta T, right? And we can easily prove this relation that alpha is to beta is to gamma is just 1 is to 2 is to 3. Okay, so alpha is to beta is to gamma is what? It is just equal to 1 is to 2 is to 3, right? This thing is clear, everyone? Okay, we just need to remember this. And for an example, you can take, for an example, you have this area. So it has length and breadth. So area is what? Length times breadth. Area of a rectangle is length times breadth. So you can say change in area per unit original area is what? Change in length per unit original length plus change in breadth per unit original breadth. Here it should be delta B by B. Okay. So then, or I can take, let's say I take a square like this. What is its area? It is length square. That means L times L. Okay. So what is delta A by A? So we know from the first chapter it would be what? Because A is equal to L square. You have delta A by A is equal to 2 times of delta L upon L. So what is delta A by A? It is equal to beta delta T. Okay. What is delta L by L? It is equal to alpha delta T. So you have beta delta T. This thing is beta delta T is equal to 2 times of alpha delta T. Right, delta T gets cancelled out. So beta is equal to 2 times alpha, right? And therefore what would be alpha is to beta? 1 is to 2. Right? Yes, no? Okay. So we can very easily find out this relation that alpha is to beta is to gamma, 1 is to 2 is to 3. Okay. So let's just remember this. All right. So now let's see some problems based upon this thing. So on a new scale of temperature, which is linear and called as W scale, okay, some W scale, the freezing point and boiling points of water are 39 degree W and 239 degree W. Okay, so now the good thing about this is you can design a scale after your name. Okay, so you can just say that I don't like Celsius scale, I don't like Fahrenheit scale. Okay, so just like there is a W scale in question, okay, you can design a scale on your name, right? So what do we just need to do is you need to plot the relation between the W scale or whatever scale that is with, you need to relate it with either Celsius or Fahrenheit, right? So in question they wanted to relate it to Celsius scale, right? So now we want to relate W scale. So we'll draw a graph similar to what? The graph between Fahrenheit and degree Celsius. So this will be W, temperature in W scale, and on x-axis we have temperature in degree Celsius, right? So what do they say? The freezing and boiling points of water are 39 degree W. So this is 39 degree W, 39 degree W is the freezing point, which is 0 degree Celsius, right? And boiling point is 239 degree W. So 239 degree W. Okay. So how much is difference in these two? It is 200. So delta W is equal to what? 200. right? Or delta temperature in W is equal to 200, okay, 200 degree W. So then question is, what will be the temperature on the new scale corresponding to temperature on 39 degrees Celsius on the Celsius scale? So what will be temperature in W? TW equals to what? TC is equal to what? 39 degree Celsius. So we can very easily find out the relation between these two. So we know Y is equal to mx plus C. So what is C? So temperature in W, oh, I wrote C here. Temperature in W when temperature in degree Celsius is 0. So how much is that? 39 degree W, right? So C is equal to what? 39 degree W. So Y is temperature in W scale. It's equal to M times X. X is our temperature in Celsius plus C is 39, right? C is equal to 39. When X is 0 means temperature in degree Celsius is 0. Temperature in W is what? 39. That is freezing point. Okay, so how much is M? It's very simple. So change over vertical divided by change over the horizontal coordinate. So change over vertical coordinate is what? 239 minus 39. So that is 200 divided by 100. So that means it is just 2. Okay, so M is just 2. And then you put the value. So it is 2 times of 39 plus 39. So 3 times of 39. So 43s are 120. That means it is 117. 117 degree W, right? So it's option D. Is this thing clear, everyone? Yes, no? All right, good. Then let's see next one. A centigrade and Fahrenheit thermometer is dipped in boiling water. The water temperature is lowered until the Fahrenheit temperature registers 140 degree Fahrenheit. What is the fall in temperature as registered by centigrade thermometer? Okay. So first of all, find out the temperature in degree Celsius. So temperature in Fahrenheit, we know it is what? What's the conversion factor? 1.8 times temperature in Celsius plus 32, right? And then it's given that this thing is 140. Okay. The Fahrenheit thermometer registers 140. So this is 140. It's equal to 1.8 Tc plus 32. Take this 32 on this side. So 140 minus 32 is 108. So Tc, 1.8 Tc, 1.8 Tc, temperature in Celsius is 108. So divide that with 108. So 1080 divided by 18. How much would that be? 1080 divided by 18. I want to find out. Or it is 540 divided by 9. And this will be 60, right? So temperature in Celsius would be 60 degrees Celsius. Okay. But the question is, what is the fall in temperature as registered by centigrade thermometer? Okay. So it was in boiling point, in boiling water, and then the temperature becomes 60 degrees Celsius. That means it goes from 100 to 60. So what is the fall? Fall is 40 degrees Celsius. Is this thing clear, everyone? Right. Okay, good. So there will be questions like this. They asked one question in 2008, then I don't know actually, but very few questions are asked based upon this, but that doesn't mean it's there in syllabus, so there can be questions, right? Okay, so it's 8:45, and just because we have seen the linear expansion, volume expansion, let's just see one question. Okay, this is from NEET 2019. Okay, we'll see one question and we'll stop. Okay, NEET 2019. So a copper rod of 88 centimeter and aluminum rod of unknown length have their increase in length independent of increase in temperature. So delta L is independent of increase in temperature. Okay, the length of aluminum rod is, this is the question, copper rod has length equals to 88 centimeter. So what they have given, actually in the original question it's their increment is same. Okay, it is same, this is given in the original question. Okay, so if they have same increment in length, so delta L for copper is equal to delta L for aluminum, right? And what is delta L? So we know that delta L is equal to alpha or L naught times alpha delta T, right? So L naught for copper, or let's say L only, L for copper times alpha of copper delta T should be equal to what? L for aluminum times alpha of aluminum times delta T. Okay, so this thing will get cancelled out. Delta T gets cancelled out. And then what is given? Length of copper rod is given. So length of copper rod is given. We want to find out length of aluminum rod. So length of aluminum rod just equal to what? Length of the copper rod times alpha of copper divided by alpha of aluminum. So very simple question. Okay, so length of copper rod is 88 centimeters. Then alpha of copper is 1.7 multiplied by 10 raised to minus 5, and this is 2.2 multiplied by 10 raised to minus 5. So 10 raised to minus 5, 10 raised to minus 5 gets cancelled out. 88 divided by 2.2 is what? 44? No, not 44, 40, right? If you multiply this thing by 10, and this thing becomes 22. So multiply this thing also by 10. So 88 divided by 22 is 4. 40 is 40. So 40 times 1.7. How much is that? 68. Right. So 68 is the answer. Okay. So answer is option A, 68 centimeters. Is this in clear? Yes, no? So let us see this next problem. The coefficient of linear expansion of brass and steel rods are alpha 1 and alpha 2. Lengths of brass and steel rods are L1 and L2 respectively. If L2 minus L1 is maintained same at all temperatures, which one of the following relations holds good? Okay. So L2 minus L1 is maintained same at all temperatures. This is given, right? Remember, we have this formula that delta L is equal to what? It is equal to L naught multiplied by alpha delta T. So let's write it for brass. Okay, delta L for brass would be equal to what? L naught for brass. Okay, L naught for brass, let's say L naught B alpha delta T. Okay, delta T is change in temperature, and delta L for steel is equal to L naught for steel multiplied by alpha delta T. Okay, so now what is delta L for brass? So delta L for brass, it is final length for brass. Okay, it is final length for brass. So how do we write it? Let's write it as LB minus L naught B. Okay, and that is equal to what? And if you take that L naught B on other side, you can write LB is equal to L naught B plus L naught B multiplied by alpha delta T. And similarly for steel, you can say that length of steel rod is equal to length of steel rod at 0 degree Celsius plus length of steel rod at 0 degree Celsius multiplied by alpha delta T. But here it will be alpha of steel and here it will be alpha of brass, right? And then you subtract one from another, right? Lengths of brass and steel are L1 and L2. So length of steel is L2. So subtract length of brass from it. So subtract, let's say this is 1, this is 2. Subtract 1 from 2. So you get LS minus LB. This is your L2 minus L1, right? It is equal to L naught S minus L naught B. And they say that it is maintained same at all temperatures. That means this is equal to this thing. Okay. Then we are left with still this thing. So plus you can take delta T common. So L naught S multiplied by alpha S minus L naught, it was L naught B, no, sorry, I wrote L naught alpha, L naught B multiplied by alpha B, okay, times delta T. And if this thing is equal to this thing, okay, the length difference between steel and brass rod, it is same at all temperatures, means this thing is equal to this thing. So we can just get rid of it. We can just cancel it out. And then we get this thing is equal to 0, meaning what? So we can just divide 0 by delta T, it is 0. So length of steel multiplied by alpha S at 0 degree Celsius, it's equal to length of brass times alpha B, or you can just say that length of steel rod times alpha S is equal to length of brass rod times alpha B. Okay, so this is L2 alpha 2 and it should be equal to L1 alpha 1, right? So it is option B. Okay, is this thing clear, everyone? Okay, good. All right. Then let's see next one. The value of coefficient of volume expansion of glycerin is 5 multiplied by 10 raised to minus 4 per Kelvin. The fractional change in the density of glycerin for a rise of 40 degrees Celsius in its temperature is. Okay. So value of coefficient of volume expansion is given. It is 5 multiplied by 10 raised to minus 4. So gamma is given. So gamma is equal to what? 5 times 10 raised to minus 4 per Kelvin, right? Per Kelvin. And the fractional change in the density of glycerin for rise of 40 degrees Celsius in its temperature is, right, we want to find out fractional change in density. That means we want to find out delta rho divided by rho. Okay, so what would be the relation between this delta rho by rho? See, how can we write this thing? So delta V by V is equal to, I can say gamma times delta T. Okay, I can say it is equal to gamma times delta T, right? Because gamma is the coefficient of volume expansion. So gamma times delta T. Okay, then you know that density is mass upon volume, and when you heat the substance, its mass will not change. So you can just say the density is inversely proportional to volume, and therefore delta rho by rho is just equal to, using the formula in the first chapter, we can just say that delta rho by rho, it is just equal to what? Minus of delta V by V. Okay, so this thing can be written as minus of delta rho by rho. Okay, and take that negative sign on other side. So you get delta rho by rho is equal to minus of gamma delta T, right? And then put the values. So gamma is 5 multiplied by 10 raised to minus 4 multiplied by change in temperature is 40 degrees Celsius. So put that 40 times 5 is, how much is it? 200. 200 times 10 raised to minus 4 is 2 multiplied by 10 raised to minus 2. Okay, so that should be the answer. So minus 2 times 10 raised to minus 2. So that means 0.02. So it is option D. Okay, the negative sign just tells us that if temperature increases, what will happen? The density will decrease. Right? Is this thing clear? Okay, good. So this is very simple, right? Okay, let's see next one. The density of water at 20 degrees Celsius is 998 kg per meter cube, and at 40 degrees Celsius it is 992 kg per meter cube. The coefficient of volume expansion of water is. So we can just make use of this formula, right? The delta rho by rho is equal to minus of gamma delta T. Okay, and then we can substitute delta rho is what? Rho 2 minus rho 1 divided by rho 1. Okay, and it's equal to minus of gamma multiplied by, we get here it will be T2 minus T1, or we can absorb that negative sign inside the bracket and we can write this thing as gamma times T1 minus T2. Okay, so I have absorbed this negative sign inside the bracket. Okay, so this is simple. Sorry. Okay, let's I'm sorry. So let's then put the values. So what is rho 1? So first temperature is 20 degrees Celsius, second one is 40 degrees Celsius. Okay, actually we should have done it other way around. Let's keep it minus gamma delta T only. Okay, so this is T2 minus T1, and we'll take negative sign on other side. So T2 is 40 degrees Celsius, T1 is 20 degrees Celsius, right? So let's put the values. So this is 40 minus 20. Okay, and then it is 998 at 20 degrees Celsius. Okay, and 992 at 40 degrees Celsius. This is 992 minus 998, and in denominator you have rho 1, which is 998, and then 992 minus 998 would be 6, right? 6. So minus 6. So this thing is minus 6, that negative sign gets cancelled out. Okay, so you have 6 divided by 998 is equal to gamma times 20. So then move 20 on other side, 2. So we'll get gamma is equal to 6 divided by 998 multiplied by 20. So this thing is 3. Okay, 3 by 10, and this is nearly 1000. So this is 3 times 10 raised to what? Minus 3 minus 1, that is minus 4. Okay, so it should be 3 times 10 raised to minus 4 per degree Celsius. This is the answer. Right, this is clear. All right, good. Let's see next one. The quantities of heat required to raise the temperature of two solid copper are in the ratio. All right, we'll see this. Sorry. Quantities of heat required to raise the temperature of two solid copper spheres. Okay, so before that we need to learn something. Okay, so there is one more thing. So water shows some anomalous behavior. What is anomalous behavior? Means strange behavior. So generally, see, what should happen if you increase the temperature of a substance, anything, then what will happen? It will expand. If you decrease the temperature, then it will shrink. Okay, its volume will decrease, right? That means density of substances goes on decreasing as you increase the temperature because volume is increasing, and density of substances goes on increasing if you decrease the temperature. Okay, but for water it shows highest density at 4 degrees Celsius. Okay, it shows highest density at 4 degrees Celsius. That means even if you increase the temperature from 4 degrees Celsius, still it will expand, okay, and its density will decrease. And even if you decrease the temperature beyond that, that means minus okay, 3 2 1 etc. Okay, so from 4, if you make the temperature 3 degrees Celsius, 2 degrees Celsius, 1 degree Celsius, 0 degrees Celsius, still what will happen? The density will decrease. Okay, it will expand, right? This thing is clear. So this is called as the anomalous behavior of water. Okay, density of water is highest at 4 degrees Celsius. Oh, and it decreases. The density of water decreases even if you increase the temperature and you decrease the temperature from 4 degrees Celsius. Right? So this is called as the anomalous behavior of water. Now, one application of this thing is it saves the water life. Okay, so life inside the water in lakes, seas, okay, lakes, etc. It saves the water life. Okay, so suppose this is a lake, then what happens here is in the winter season, now what will happen? The temperature goes on decreasing, right? So temperature in the lake will decrease, so lake water temperature will decrease. So now as temperature decreases, what will happen? So see, this topmost layer of water, it is in contact with the surrounding, so its temperature falls down, okay, earlier compared to this lower part of water, you can say. So now its temperature goes on decreasing. So suppose it goes till 5 degrees Celsius, then it will go to 4 degrees Celsius. So as it goes to 4 degrees Celsius, then what happens? Density of that water would be more compared to that of, let's say, the temperature of a layer which is just below it, it is 5 degrees Celsius. Okay, so then what will happen? If density is more, then this water which is at 4 degrees Celsius, okay, it will shrink, right? But then after that it will shrink, sorry, what did I say? Shrink. It will sink, okay, and after that what will happen? So see, now temperature falls down, so it becomes 3 degrees Celsius, okay. So now temperature of water below it, it is suppose 4 degrees Celsius, and temperature over here is 3 degrees Celsius. So what is density of this thing? Density of top layer, it would be less than the density of a layer which is just below it, right? So because density is highest at 4 degrees Celsius, so if temperature decreases even further, so density is not going to increase. That means this water will not sink, okay, and new water will not come up. So that layer will remain there only, okay. So only the temperature of topmost layer will go on decreasing, right, and it will solidify, okay, at 0 degrees Celsius. Its temperature will go on decreasing beyond that too, but temperature below that will be more, it will be 4 degrees Celsius. Is this thing clear? Yes, no? There would be some internal conduction also, but if you forget about that, then temperature below this top layer would be higher, and that's why the life here will be saved, okay, the plants and animals, right, fishes, etc., not animals, they will be saved. Is this thing clear, everyone?